Hello and welcome to lecture 22 of Math 2R03. In today's lecture, we're going to be looking at the decomposition of an operator. And just to to preface today's lecture, I should mention that today we're going to really spend a lot of time on the theory, and in lecture 23, I'll work out a very detailed example. So lecture 23 is actually just a specific example of a lot of the things we're talking about. So you may want to look at today's lecture and then jump to lecture 23 so you have both the theory and the example in front of you to kind of help you with this material. And so let me just kind of first set up the situation we want to look at. So remember, kind of our goal is to do something like this. So if we're given an operator, can we decompose our vector space so that V is a direct sum of subspaces such that T is invariant on each of these subspaces? Now, we've already proved that you can do this if V has a basis of eigenvectors. Say that V1 through Vn is your basis, then V can be written as the direct sum of span of V1, direct sum span of V2, and so on. And depending on your operator, or the operator that corresponds to this, it's invariant on each of these subspaces. But from what we've seen, right, this actually we may not be able to always do this, even if we work over the complex numbers, right? So however, the problem is that T may not have enough eigenvectors, okay? So for example, this could happen if T is not diagonalizable. We don't have enough eigenvectors around. Okay, so maybe I'll actually write this, right? So we don't have enough eigenvectors to kind of do this trick up here. So the question is, can we fix this somehow? And the point of today's lecture is to show that over the complex numbers we can fix this. But instead of using a basis of eigenvectors, what we're going to do is we're going to fix this problem with generalized eigenvectors. So that's what we introduced in the last couple lectures, which is generalized eigenvectors. And these are going to be the things that we're going to use to kind of do an analog of this blue result up here. Okay, so make myself disappear and just kind of like get things set up. We need one little lemma that I'll use kind of throughout the lecture. And the first lemma says that if I take any linear operator and if I take any polynomial with coefficients in the field f, then T is invariant on both the null space of the polynomial of the operator applied to the polynomial and the range of that same operator. So in other words, if I take a vector in the null space of the operator I get after applying a polynomial to it, and then I evaluate V at T, I get something back in the null space. And same thing for the range. If I take something in the range and I plug it into T, I go back into the range. So the theorem that we want to kind of look at, which kind of fixes this problem that I have over here, is this one, written in black, which says, let V be a vector space over the complex numbers, and let's take a linear operator. And then let's say that you look at the distinct eigenvalues, and we know that it has eigenvalues because it's over the complex numbers. And then V can be written as a direct sum of generalized eigenspaces. These are the generalized eigenspaces. Moreover, T is invariant on each of these eigenspaces. And one thing that we'll need later on is if you look at the operator that we get by looking at T minus lambda I lambda I times the identity operator, and we restrict it to each of these eigenspaces, each of those guys are nilpotent on the corresponding space. Okay, so there's a lot here to unpack, and let me in this part just kind of do part 2 and 3, and then when we come to the next part of today's lecture, I'll talk about part 1. Okay, so part 2 and 3 are actually not so difficult to prove. So for part 2, just remember that by definition, the generalized eigenspace of lambda I is T minus lambda I to the power of n. That's the definition. And what we want to do is now make use of the fact that this is equal to the null space of PT, where we're taking our polynomial P to be the polynomial Z minus lambda I raised to the power of N. Okay, so then by the lemma, T is invariant on the space G lambda I T, because T is an element, T is being invariant on this space right here, but so it's an invariant on the null space of this polynomial, this operator coming from this polynomial. And similarly, let's check that if we restrict to the vectors inside the generalized eigenspace, that this operator is nilpotent. Okay, and to see that, let's say we take a vector inside of this space. Well, that means that when I take t minus lambda I to the n times v, I get that this is equal to 0. And this is true so for every vector, right? So t minus lambda I times the identity operator is nilpotent on the subspace G lambda I T. So when we restrict to this space, everything here gets sent to the 0 vector. Okay, so I'm going to pause here, and then when we come back, we're going to talk about part 1 of this particular theorem.